So the first thing we want to do when we are graphing a piecewise function is identify what the domain restrictions are. And so these are the domain restrictions. In fact, I should write that. The domain restrictions. It's this way for every piecewise function. You have certain values for x that you're allowed to use the first piece, and then other values for x you're allowed to use the second piece. So the graph will behave according to which piece you are on currently. So the x values that are less than 0 are all of these. Okay, and then the x values that are greater than 0 are all the ones over to the right of the x-axis or of the y-axis. Okay, so when x is less than 0, we want to graph y equals x minus 1. Well, y equals x minus 1, the next thing we want to do is figure out, well, what does the graph look like? What does y equals x minus 1 look like? Well, it's a straight line. It's a linear function. The slope is 1. The y-intercept is negative 1. But we're only allowed that graph when x is less than 0. So the graph would have a slope of 1. And then when you get to x equals 0, the y value would be negative 1 if it went through the y-axis, but it's not negative 1. There's an open circle there because of that guy right there. So when x is less than 0, the graph of y behaves like y equals x minus 1. And then likewise, when x is greater than 0, the graph of y, which is made up of these two pieces, behaves like y equals x plus 1. Still a slope of 1, but now we have a y-intercept of positive 1. So the graph of the second piece would follow this line, y equals x plus 1. And just like down here, when x is equal to 0, we have an open circle. Then we have a slope of 1, up 1 and over 1. And this graph is the graph of y, which is made up of two pieces, x minus 1 and x plus 1. All right, so let's take a look at this next one. Y equals x squared minus 1 when x is less than 0. So we have to ask ourselves, well, what does x squared minus 1 look like? Well, if this quadratic function didn't have any domain restrictions, then it would be still a parabola, but it'd be a parabola would have no, the domain would be all real numbers. So it would have a y-intercept of negative 1, and it would be a parabola. Okay, but we're only allowed that part of the parabola when x is less than 0. So again, we get our open circle, and then we have this parabola to the left of x equals 0, and that's the first piece of this piecewise function. So the function is y. So y is the function made up of two pieces. Okay, and then when x is greater than or equal to 0, the function y behaves like 1 minus x squared. Well, 1 minus x squared is also a parabola that has a vertex of 0, 1. So it's y equals x squared flipped over the x-axis and then up 1. So it would look like this. Vertex would be 0, 1, and it would open down because the a is negative. And this one, this piece, is defined when x is equal to 0. So we would actually have a point right there at x equals at the point 0, 1, and then we would have the parabola opening down. Okay, and that's it. So let's see if we can squeeze these other two in here. Now we know what y equals 1 over x looks like. I'll start doing my graphs in pen and blue. So y equals 1 over x is up in the first quadrant and down in the third quadrant, but we're only allowed to use this piece when x is less than 0. So we'll just draw the graph like that. We do also have a horizontal asymptote, which only really matters when x is less than 0. And we also have a vertical asymptote. So the graph of y behaves like 1 over x, but when x is less than 0. Now, because we have a piecewise function, you might be thinking we can never touch the vertical asymptote. Well, that's for all rational functions. No rational function are you able to touch the vertical asymptote, but all bets are off when we're dealing with piecewise functions. Piecewise functions, we have a rational piece, and then we have a constant piece, and that's what we have here, y equals 3 on the interval from 0 to 2. Okay, so on the interval from 0 to 2, including 0 and including 2, y equals 3. So we are allowed to touch a vertical asymptote, but again, not on a rational function only, but on a piecewise function, we're allowed to do that. And then on the interval from, when x is greater than 2, for all real numbers greater than 2, the y coordinates, or the y values, are all equal to -2. And we would put an open circle when x is 2 at -2, and we would have the graph of y would be a constant, another constant of -2 for all x values greater than 2. And then finally, we have between 0 and 1. Let's make that 1 a little bit bigger there. So between 0 and 1, the graph of y behaves like y equals radical x. And so we know what y equals radical x looks like. And when x is equal to 0, square root of 0 is 0. When x is equal to 1, the square root of 1 is 1. But we have an open circle there, and it behaves like this. It's not a straight line, it's that curve. So y equals radical x for that piece. And then when x is greater than 1, y behaves like the y equals -x. And y equals -x is that diagonal line at the 45-degree mark between the second and the fourth quadrants. So if you follow that down, if you're ever in doubt, just plug in for x the endpoint of the interval. So if you plugged in x equals 1, y would be -1. Okay. Now, I know it says x is greater than 1, right, but the endpoint of the interval at 1, -1, we would have an open circle. We would have a hole in the graph, open circle. Then we would follow, so when x is 2, y is -2. When x is 3, y is -3. So 2, -2, 3, -3, and the graph of y would behave like this function, y equals -x. And if you want to think about that as if you put it in mx plus b form, you have -1x plus 0. Slope of -1, y-intercept of 0. So that's exactly what it would do if you didn't have this domain restriction on it. So there you go.